Hooray, the Labrador Sea. This is the Labrador Sea. Okay, examples from the Labrador Sea. You cut through the Labrador Sea. You can see it is a deep basin, exceeding 3,000 meters. Okay, what you do also, in order to see three distributions, you actually compress the horizontal scale. Okay, what's actually shown here is 10 degrees is about 1,000 kilometers, is the horizontal scale of each of these graphs, and only 3,000 meters the vertical scale. So it's highly distorted, the representation. But anyway, have a look at it. The left figure shows you the temperature structure, the middle one, the salinity structure, and the right panel shows you the dissolved oxygen in milliliters. And what you can see here is a typical feature of deep convection in the open ocean. Here, look at the salinity. You can see it's fairly homogeneous down to depth of 1,500 meters. Okay? And some years you get the convection down to 3,000 meters. Okay? So how can I say that? Do you believe me? Well, I can tell you, just look at the dissolved oxygen distribution. You can see how high it is, 6.8. Okay, so you learned that minimum oxygen, these dead zones have numbers of below 2 milliliters per liter, and here you have 3 times enough oxygen in there, and it goes down to the bottom. And the only process that can generate oxygen at depth is the mixing from the surface to the bottom of the ocean, and in some years you have it. In this example, you have evidence of deep convection, or maybe to 1,500, 2,000 meters, something like that. Okay? You can see the same in the temperature. You have that big signature, the yellow regions here on the left. Okay, the yellow region here on the left, 3.5. So now what we want to do is we want to have a look at the spreading of this water, not of the deep western boundary current that is created, that comes from the Labrador Sea as part of the North Atlantic deep water. We want to have a look at the spreading of what happens to the water at 1,000 meters. Okay, you can see at 1,000 meters you have a temperature of 3.5 degrees and a salinity 34.9. And now you can have a look at all observations that you have in the Atlantic Ocean at a depth of 1,000 meters horizontal. Let's see whether you can identify the spreading of this water. Where does it go? And this is shown here on the next slide. So you're in the North Atlantic, 20 degrees north of the equator to 65 degrees north. This is shown here. North Atlantic. On one side is North America, on the other side is Africa, and you probably can identify Portugal and Spain is up here, Norway on the top. And this is now shown at 1,000 meters. Left is temperature, the right is salinity, horizontal distributions, 1,000 meters, and you can see that there is a spreading. It's spreading along the continental margin, and you have a spreading also to the eastward spreading. Okay, and this is how you can follow water masses. So by the way, you can see another water mass here, and we talk about this region in some 10 slides ahead, and this is the outflow from the Eurafrican Mediterranean Sea. You can identify, and have a look over my head here. 36 is hypersaline water at that, and you can see a tongue of that water spreading over to the west. And we talk about that later on. Okay, that's quite interesting that you get these structures in the ocean. And I say it again, it's only because both salinity and temperature control the density That's why we know so much about what happens in the ocean interior. If we only had temperature and not the salinity effect, we would not be able to do that.